So in this video, we're going to take a further look again at the modulus and conjugate of a complex number and see some of the sort of questions we can have around these two things. Okay, so explain with illustration why z minus z star is always purely imaginary or zero. Now, before we do this, I'd much rather do this algebraically, okay, rather than with an illustration. We'll look at that illustration in a moment. But let's just think about z being a plus bi. That's some generic complex number. Well, that would make z star, its conjugate, equal to a minus bi. Now, so let's see if we can think about what z minus z star is going to be. Well, of course, it's going to be a plus bi, which is z, minus a minus bi, which is z star, right? So can we simplify that? Of course we can, because if we think about that real component, we'll have an a and a minus a. And if we think about that b component, where we're going to, the imaginary component, we'll have a bi and another bi, won't we? Because the minuses will kind of cancel out. So we'll have 0 there as the real component, and we will have a plus 2bi as your imaginary component. So overall, I guess if you're writing this as a final answer, what is it? It would be 2bi. Now, let's look at that question again. Why is it purely imaginary or zero? Well, we've just proved that it's always imaginary. Look, you can see why, because the real part cancelled out. We're only left with an imaginary component. That's why. It could be 0, because if b itself started off being 0, then that would make the whole thing 0, wouldn't it? Right? So it could be 0, but the other option is it's purely imaginary for any other real number b. So let's now think of a diagram, okay, as the original question says. We've already proved this is true, but let's just imagine a diagram on the Argand plane. So if I imagine, let's draw it out, we've got my imaginary axis, and we've got my real axis, right? There they are. Let's draw what z could look like, right? Okay. Well, z, there it is, right? I'm just making it up. It could be 3, 2. Doesn't really matter. We don't even need those squares, right? Okay. But z could be that. Well, of course, that would mean that z with a little star is one of those, right? But we're dealing with vectors here, and you may not know a lot about vectors, right? But if I wanted to add these things together, I could really pick that thing up and then put it on the end of the of the z, right? So if I wanted to draw a representation, let's just do it sort of separately over here, perhaps. Okay, using those particular values, though, of course, right? If I wanted to have a z, it's again just like that. But if I was going to add on to that a z star, right? Okay, sorry, excuse me, not add on. I think our question asks us to do z minus z star. So if we're going to take away a z star, right? Well, that's going to be like a z star, but going in the wrong direction, right? Okay, so a minus z star is going to be going back the other way, like that. That's like a minus z star. And there's my z. So where does that end up? Well, what's happened then, the kind of resultant vector takes us there, look, okay? That is z minus z star. And of course, it's purely imaginary, isn't it, right? It's on that imaginary axis. That's the diagrammatic sort of reason why that is true. Okay, now let's carry on and have a think about another one. So explain using an Argand diagram why for all complex numbers z and w, we've got z plus w star is z star plus w star. Now, I'll come to that diagram again in just a moment. But before we go any further, let's just see if we can do this algebraically. So can we prove those two things? So I think this time we'll say that z is equal to a plus bi. And w is equal to c plus di. And a, b, c, and d, they're just numbers we don't know. We could sub in anything there. Look, okay, we're kind of show something in a general sense right now. Okay, so let's take a look at our question. First of all, let's think about what z plus w star is going to be. Well, z plus w star, let's put in some values for z and w. So a plus bi plus c plus di star, right? And of course, we can move around those components. So we're going to have a plus c as our real component, and plus a b plus di, look, as our imaginary component. Now, if I want the conjugate of that, and that's with the star there, look, I just need to invert the sign, don't I? So that is going to be a plus c minus b plus di. Okay, that's it. Right, okay, now then, so can we try now? Okay, that's our z plus w star. Can we try and show that it's equal to z star plus w star? Well, I hope we can. Let's see if we can engineer this correctly. So again, we can kind of write this out again in more components, right? A plus c, we've got a minus bi and a minus di. Well, we could write the a and, we could write that a and the minus bi together. And we could write the c and the minus di together. And of course, a minus bi, if z, remember, was a plus bi, well, that is z star. And, well, if w was c plus di, what we've got there, c minus di, is w star. So we've done it, look, we've proved. We started off up here, look, with z plus w star. We've proved it's z star plus w star. Okay, so that's a nice proof there. Look, now then, let's again focus in on the Argand plane and take a look at what that could mean. So I've already drawn out for you, look, what z plus w looks like. I've just made up some vectors, that red vector z and that blue vector w. You can see overall that black line there, look, that's z plus w. So if that's z plus w on our Argand plane, right, well then what would z plus w star look like? Well, that is going to be a reflection, as we already saw in a previous video, okay, in that axis there, look, okay, so that is got to be z plus w star, because it's a reflection in that real axis. Okay, so next thing to say then, well, is that z star plus w star? Well, let's draw out a z star. So a z star is a reflection of z, right? So that's going to be something that looks like this, right? It's going to be a reflection in that real axis. Okay, what about adding to that a w star? Well, you can see w up here is 1 across and 3 up. So we're going to need to go 1 across and 3 down. Yeah, absolutely right. Okay, you can see here quite clearly that z star plus w star is z plus w star. So that is the Argand diagram explanation for that proof. Okay, now we've talked a little bit there about conjugates and that property that they reflect in the real axis. Let's take a look now at some modulus stuff, right? Now, I'm not going to go through every single one of these, and please don't panic if you don't understand everything here. But let's just take a little thing and make sure we understand some of this, right? So first of all, let's take this top line here. Now, remember what the modulus is, okay? That is going to be a squared plus b squared square rooted if z is a plus bi, right? Okay, it's the length of the line, all right? So think about it from a geometric perspective, perhaps, okay? Just that first one there. If we have the z there, look, well, that length is going to be the same thing as the length of z star, right? This has got to be true. And if I have the length and I square it, it's going to be the same thing as the original times the modulus squared, because they're all the same lengths, right? This is making lots of sense. So we can prove some of these facts, and you can use some of these facts, but these things you can see right here on that page are all true. Now, let's finish off with a really complicated problem. Okay, let's do a proof, right? I think that this one was here. Look, it's the third one down. Okay, let's actually have a go at proving something. We're going to prove that the modulus of z1, z2 is equal to the modulus of z1 multiplied by the modulus of z2. I don't think that's that obvious, so we'll have a go and see if we can do it. Okay, so to start with, let's make up some general expressions for each of these complex numbers. So we'll say that z1 is a plus bi, and we're going to say that z2 is c plus di. Okay, so I think that we better start off with that left-hand side. First of all, before we even go there, I suppose we better start by thinking about just what z1, z2 is, right? Well, that's going to be a plus bi multiplied by c plus di, okay? Now, again, I'm going to write it all out, I think, just so you can see every part of this. And I'm sorry if you can easily do this at this stage. So what we're going to have an AC, a BCI, and an ADI, and we're going to have a minus BD. So that was a BCI there. Okay, so therefore, our modulus of Z1, Z2 is going to be, actually, well, there, look, is our real component, okay? So it's going to be AC minus BD squared, and then our imaginary component is the collection of these two things, right? Okay, so it's going to be plus AD plus BC squared, square rooted. Okay, so we can do those. I think I'm going to use the multiplication grids again to work these out nice and smoothly with the minimum of fuss. Let's just write them out there. Look, AD plus BC, AD in a plus BC. Okay, so we're going to have A squared, C squared. We're going to have a minus ABCD, a minus ABCD, and then a positive b squared d squared there. On this right-hand side, we're going to have a squared d squared, a, b, c, d, a, b, c, d, and then b squared, c squared. Right, okay, so our modulus of z1, z2 is going to become the square root of, right, let's write this out. And so we're going to have a squared c squared minus 2abcd plus b squared d squared plus a squared d squared plus 2abcd plus b squared c squared. Wow, this is a complicated one. Okay, what can we do from there? Well, straight away, we're going to cancel some stuff out. I can see a minus 2abcd and a positive 2abcd. So from there, what we can do is we can write this out again. I think I'll save that square root to the end. Let's have the a squared c squared plus the a squared d squared on to start with, plus b squared d squared plus b squared c squared. Okay, all being square rooted. Okay, what next? Well, I'm going to start to factorize this up into little sections. I can put those first two terms together. A squared open bracket c squared plus d squared, and then on the right I can say b squared open bracket c squared plus d squared. And then of course, if I've got a squared timesing c squared plus d squared, and I've got b squared timesing c squared plus d squared, then overall what I've got is, and this is the clever bit, a squared plus b squared multiplying c squared plus d squared. Okay, everyone following this? I hope so. Now then, now I've done that, I can split apart my square roots because I've got multiplication. So what I can say is I've got the square root of a squared plus b squared multiplying the square root of c squared plus d squared. And you know what? Let's just bring it all the way back to the beginning. Remember, look, okay, what z1 was? It was a plus bi. So the modulus of z1 would be a squared plus b squared square rooted. Well, that's what we've got. So we've got the modulus of z1. Let's go back to the top. Can you see z2 is c plus di? So the modulus of z2 is going to be c squared plus d squared square rooted. That's what we've got, look, right? So we've got it. There we go. So don't forget what we were doing, guys. We have started with the modulus of z1, z2, and proven that it is the same as the modulus of z1 multiplied by the modulus of z2. Now, I'm not expecting you guys to all be able to do that, but I want to show you some challenging math and a nice proof there, look, okay, and that is a really good one. So hopefully, look, you have had a quick, more experience now working with that conjugate, understanding some of the properties and that modulus function, okay? I just want to emphasize, if you see anything here, look, okay, on this page, you may be able to use it in some of your questions.